Hey, we have here today on the board a tricky looking integral. We've got the integral from 0 to 3 pi over 2 of sine 2023 x dx. Okay, so what we obviously need to deal with is some kind of power reduction. We have this huge exponent on the sine function. What I want to do is just kind of go through all the steps and see how we derive things and how we get to the bottom of a problem like this. Okay, so what I've added here on the board is this kind of generic power reduction formula for integrals of sine. And this is useful when we have larger powers like what we have here. We can reduce the power if we have an integral sine to the nx. We can reduce it by 2. So we have another integral of sine n minus 2, and then we'll have this other value. Now, if this was like sine to the 6th or sine to the 7th or something, if it was reasonable, maybe we could just use this. We could just iterate, do it, whatever, 3 or 4 times. Maybe it takes a little while, it's tedious, but we could get through it. With 2023, we're not going to want to try to integrate this 1,000 times or whatever. But this formula can still help us, and then let's look at what happens. This is for an indefinite integral. Let's look at it for our case of a definite integral. Okay, so now what I've done is I've put in our bounds, our 0 to 3 pi over 2 in each of these cases, and then also here. I've still left the power as n, so we're not concerned if we're dealing with 2023 or 100 or what. The thing I want to notice here, let's just look at this piece and look at what happens. So if we try to evaluate this, not even worrying about what n is, at 3 pi over 2, sine of x is going to be -1, cosine of x there is 0. So just looking at this, we're evaluating, we have a 0 for our first piece. Minus, then we look at 0, cosine's 1, but then sine 0. So we have another 0. And it turns out that what's going to happen is, as long as our boundaries are multiples of 90 degrees, pi over 2, pi, 3 pi over 2, 8 pi, etc., this is always going to be 0, because at those points, at every 90 degrees, one of either sine or cosine is going to be 0. They're going to multiply to be 0. So essentially this term, in our case, is just going away to 0. Then essentially what we have is we just have a slightly condensed formula. We still have a formula where we're going to have to integrate over and over again, decreasing the power by 2, but at least we've removed this term. Next, from here with our condensed form, we can start looking at our specific case. We're calling this I sub 2023 for our sine with the power of 2023. We have a formula for this, so let's just look at what happens. If we plug this in, we know what our n is, 2023. So n minus 1 is 2022 over 2023. And then for this integral, we could look at this piece here as just this reducing the power by 2. You can look at this as I 2021. And then from here, we could just do the same thing again. What is I 2021 going to be? This isn't really helping us much, but then we have a value. We can write this as n minus 1, 2020 over 2021 I sub 2019. And then we can just repeat this for I sub 2019 to get to I 2017, and then do it again for 2017. Now you can see that, again, if our n was like 7, we'd get to something we can calculate pretty quick. But with I being 2023, doing this is going to take us forever. So we need to find a different way to approach it. From the last step, noticing that wasn't really going to work to just iterate over and over again, what I wanted to do next was try to start from the bottom. Let's just look at, instead of starting at 2023, let's start at 0. So I sub 0, and let's just look at exactly what that is. This will be the integral from 0 to 3 pi over 2, sine to the 0x, because our n becomes 0, dx. Well, sine at 0, this is just 1 we're talking about, so we're just integrating 1. We know how to do that. That's going to be x, just evaluated from these bounds, but that's just going to be 3 pi over 2 minus 0, which is just 3 pi over 2. So this is our I sub 0 value. Okay, that's easy, so let's do the same thing for I sub 1. Again, same bounds. Okay, now looking at I sub 1, we just put in for our n a 1 there, but we know it's just sine, so I'm going to just delete that. And then we'll integrate this. Integral of sine is going to be minus cos x, evaluated from 0 to 3 pi over 2. Cosine at 3 pi over 2 is going to be 0, and then, well, a minus cosine at cosine of 0 is 1, but we have a minus on there. So minus times minus plus, and so this is just going to be 1 for our I1 value. Next, for I sub 2, let's just remember this formula. This is our I n minus 2. So we're going to use this. So n minus 1, 2 minus 1 is 1, over n is 2. So we're going to have 1/2 times 2 minus 0 is I sub 0. But we know what that is. We found our I sub 0, so that's going to be 3 pi over 2. So we're going to have, I'm going to not reduce, so we're just going to leave it like this for now. Then we'll do an I sub 3, doing the same thing, 3 minus 1, 2 over 3 for our n minus 1. Then we need our I sub 1 value, but that's just 1. Don't even need to write it, but we'll just write it so we see it. Okay, and I filled in now I sub 6 value, I sub 7 value. We could keep going, but obviously it's just going to be the same thing, but we start to see the pattern. And what I want to point out is, just looking at here at this, in our numerator, 5 times 3 times 1, if we went on, we'd have a 7 and 9. This is actually just n minus 1 double factorial. This is how, and I have other videos on the double factorial that I can link to, but it just like the factorial, but it skips a digit, so it stays, notice all these numbers are odd. And then the denominator, we have n double factorial times our I sub 0 value. And then notice here it's the same exact thing. This is n minus 1 double factorial. Well, the thing to notice here, even though we have the same n minus 1 double factorial over n double factorial in both cases, in this one, the numerator is even, and here the denominator is odd, and then over here it's the opposite. Okay, so what have we established? We found that when n is even, we have this formula for I sub n, okay, where it's n minus 1 double factorial over n double factorial times I sub 0. And that's because n's even, so it's like you're iterating. If you think if like if n was 6, you'd go from 6 to 4 to 2 to 0. And then over here, when n is odd, for the formula for I sub n, we have the same coefficient here, n minus 1 double factorial over n double factorial times I sub 1. Again, if n is like 5, you're going 5 to 3 to 1. And if you look at that previous video, we derived how we go from this double factorial to this form, and this is the even case, where we have a half to the n times n factorial over k factorial, and then just noting this piece right here is the same thing as n choose k, the binomial coefficient, so we can express it this way as well. And in this case, we've defined k to be just n divided by 2. Over here, the odd case is just a little more complicated, but it's actually kind of like almost like the reciprocal of this with a few changes. We have 2 to the n minus 1, n minus 1 2 factorial, n minus 1 2 factorial, n factorial. We can write this complicated thing here as k's as long as we define k to be n minus 1 over 2. This gives us a way to write this a little differently. Also makes it, if the numbers are reasonable, you can actually calculate it to a number or a fraction. So now back to our problem. Let's just use all this, everything we've done here, calculating sine to the 2023. We know 2023 is an odd number. So let's look at our I to the 2023. This is going to be 2022 double factorial over 2023 double factorial and times our I1 value, but that was just 1. But again, we might want to see it in this form over here as a factorial rather than a double factorial. So we can write this as 2 to the n minus 1, so 2 to the 2022 times, okay, this k number is going to be 2022 over 2. 2022 divided by 2 is going to be 1011 factorial times 1011 factorial. And this is all over 2023 factorial. And that's it. That's going to be our solution. And I don't want to try to calculate those factorials because they're going to be ginormous. Anyway, I have a few videos before this that go over the generic power reduction formula, that go over the double factorial. So I'll provide a link to all that. Also the problem, I have a quiz, the power reduction quiz, provide a link to that. And you can check that out and get some more background if you need it. Thank you for watching. Please like and subscribe. Have a good day.